This is the last video for Chapter 6 on gases, and I'm not going to do it in the same order that they have it in the book. I'm going to start off with the Avogadro's law, because that's just the effective volume and the number of particles or moles. So we're going to start that. It is 6.7, but that'll work out, I think, even better than the way they did it in the book. Okay, so Avogadro, you remember him, the fellow that started us off with the atomic masses, and we have Avogadro's number from that. So in Avogadro's law, we have a gas in a container whose volume can change, and the gas is bouncing off the walls of the container, creating pressure. Now we make the volume get larger by adding more gas to it. So you see we went from 1 mole to 2 moles, and we made the volume double as well. So this is the effect of adding more air particles or gas particles to a container. You've seen this all the time yourself with cars, automobile tires. If you want to increase the pressure in the tire, you simply add more air. And the reason the air goes into the tire to begin with, when you go to a gas station and you attach that hose from the air tank to your tire, the reason the air flows into the tire is because the tire is at a lower pressure than the air is in that compressor. And so air always flows, or gases always flow from high pressure to low pressure. And you set the air compressor to a certain pressure so that when you attach the hose to the tire, once the pressure in the tire equals the pressure on that regulator, then airflow stops. And that's how that kind of works. Now, if you look at our formula that we have, they have volume in moles in here. We could also replace volume with pressure, and it'll work just as well. So here's an example question. If we have 0.75 moles of helium gas, occupies a volume of 1.5 liters, what volume will 1.2 moles of helium occupy? Well, you notice that the number of moles went up, so therefore the volume's got to go up. So what will we get for an answer? It's going to be A, B, or C. So let's check it out. So we write down our data first. Here it is down here. Then we're going to cross multiply. And we don't really show you this in the slide, but we would have started off with our gas law, cross multiplied, and then we're going to solve it for B2. And so here we go here, we plug in our values, and we get 2.4 liters for an answer. Looks pretty straightforward. Now, I want to throw this out here at this point in time because you might see some problems in the book where they mention what's the volume of the gas at STP. And so STP means a standard temperature and pressure, so it always means 273 Kelvin, because that's what we have to use in the gas laws. And it also means any of the standard pressure units. So you probably will use either 1 atmosphere, or you might use 760 millimeters of mercury, either one of those two. So that's really all there is to Avogadro's law. Very, very simple one. Just think of automobile tires when you think of that. Now we're going to combine all these gas laws together in what we call the combined gas law. Now I've left Avogadro's law out of this because they're not going to put it that way in your book. So we start off then with a gas law that looks like it's kind of complicated, but it really has Boyle's, Charles, and Gay-Lussac's all together. So P1V1 over T1 equals P2V2 over T2. So this is a combination of Boyle's, which would be P1V1 equals P2V2, Charles, which is V1 over T1 equals V2 over T2, and Gay-Lussac, which is P1 over T1 equals P2 over V2. Now, in order to solve for this gas law, we always cross multiply like you would have done anytime you have a ratio. This is what we get when we cross multiply. Now, we get 6 factors. You can be asked to solve for any one of the 6. So I'm just going to say, let's solve it for V2, because that's the most common factor you're looking for. So in order to get V2 by itself, I have to divide out P2 and T1. And that's what I'm doing down here, but I'm going to do it to both sides. And this way, P2s will cancel out, and so will the T1s. And I'm left with exactly what I need. And then I would just go and find my values and plug them in, making sure that they have the same units so I can cancel out all those units. And this is just a table 6.6, which shows you what I was talking about a moment ago, about how all these gas laws add up to the combined gas law. All right, let's take a look at a sample problem. A gas has a volume of 675 mLs at 35 centigrade and 0.850 atms. So these 3 conditions will be our ones. What is the volume? That's our unknown V2. And they give us a new temp, notice it's negative 95 centigrade, and a new pressure. All right. So you notice that the pressure is in two different units, so we're going to have a common unit there. It doesn't have to be either one of them in particular, but it has to be the same unit. They give a centigrade, it has to be Kelvin. So down here, that's exactly what we're doing. We're changing our temperatures to Kelvin. And in this slide, the author happened to change the 0.850 atmospheres to millimeters. So now we can take our equation and solve it. So here was your combined gas law. And as I showed you in a previous slide, you'd cross multiply and then divide for your unknown. And here we go here. So this is what we have to plug in. Get out all our values and stick them in there. And that's exactly what we're doing. You notice how the millimeters of mercury cancel and the kelvins will cancel. Now when you're solving this mathematically, make sure that you multiply across the top and then you divide by both numbers. So you say divided by 802, divided by 308. If you say divided by 802 times 308, the calculator will think the 308 is up top. Here's one for you to try. So you want to read the problem, copy out the data, label it, and see if you can go through the whole thing. So you want to pause the video here now. Give this one a try. Okay, let's check out the solution to it. So here's the table with all the data. You know, we have the pressure is going up 4 times. That's a big change in pressure. The volume is going down. It's like it's, oh no, sorry, the volume's going, yep. Oh, wait a second. What do we notice? Liters. That's where they changed to milliliters. So now we compare these two. The volume is being cut in half. Temperature is 29 centigrade. You want the final temperature. Right. So we're going to have to solve it for Kelvin, and then if they want centigrade, we'll get them centigrade after that. So we start off with the combined gas law, cross multiply, and then solve it for T2. So T2 winds up equaling this. And then we'll plug everything in. Notice how all the units will cancel. And then we get 604 Kelvin for an answer. But they wanted centigrade, so we have to convert it back. Right, pretty good. Now, the last section we're going to look at is Dalton's law of partial pressures. And this has a lot of applications to medicine. You can see here a person is getting some gas, some nitrous oxide, really being worked on. Right, so partial pressure of a gas is the pressure that each gas in a mixture would exert if it was by itself in a container. So here's our example. We have 2 containers. They're the same size container, so the volumes are the same. I'm assuming they're at the same temperature. And this container has a smaller amount of molecules. This one has more. So you see the pressure in here is 2 atmospheres, and the pressure in here is 4. And so the number of particles, 8 particles versus 4. Okay. What would happen if you were to combine all these gases into the same size container? So what would happen? The pressure would simply be the sum of the 2 pressures. And that's Dalton's law of partial pressures. So it means that if you have a mixture of gases in a container, the pressure of that mixture is the sum of the individual pressures. And they call the individual pressures the partial pressures. So here's the formula for it. The total pressure is equal to the sum of the individual pressures. Pretty easy. Now this diagram kind of shows you the same thing. You know, we're at STP. We have 1 mole of pure gas in a volume of 22.4 liters. Will exert the same pressure as 1 mole of a gas in a mixture. So see how we have here 1 mole of nitrogen, 1 atmosphere pressure. They put different numbers of moles of gases, but the total is 1 mole. We still get the same total pressure. So the pressure that we get for a mixture doesn't depend on the particular gases that we have in the mixture. It's only the pressures of those gases. Now here's an example that they like to go through, and that's like scuba diving. When people are scuba diving, they're breathing a mixture of gases. Now if they just have compressed air, air is mostly N2. So what happens if somebody is down deep and they come up too fast? Well, when they dive down in the ocean, the pressure on them is really the pressure of the water, which is much greater than air pressure. And that can cause some of the nitrogen that they're breathing to dissolve into the bloodstream. If they come up too quickly, they're going to get the bends, which is really nitrogen gas bubbling out within the joints of the arms and the legs. And they call it the bends because you can't bend your arms and your legs because of the pain. And it can be fatal. So when people come up from diving deep down, they have to go very slowly. And so that as they rise, the pressure will be released and the nitrogen gas will leave the bloodstream and enter back into the tank. This slide here shows you the partial pressures of the gases in the air. So nitrogen is pretty much about 80% of the air. So then it makes up about 80% of the air pressure. So here's the pressure of the nitrogen. Here's the pressure of the oxygen. So here's 21%. And carbon dioxide, about 0.8%. All the other gases are very low. Total pressure, 760 millimeters of mercury, 100%. Now, let's say they were going to solve a problem about using Dalton's law. The law is so simple that all the problems really involve is usually give you different pressure units and you have to either add them together, or they might give you the total and they want to know one of the pressures that's missing, but again they try to mess it up by giving you different units. So that's what they're doing here. So you have a scuba tank contains oxygen with a pressure of 0.450 atms and helium with this pressure. You notice millimeters of mercury. Okay, what's the total pressure in millimeters of mercury? So what are you going to have to do? You have to convert your atmospheres to millimeters. And so that's what they're doing right down here. 400.450 atms, 760 millimeters per atm, and that's the pressure of the oxygen. And then once you get that, you can add it to the pressure and of the helium, and that's what they're doing, and that's our final answer there. Here we go. My circle didn't work out too well there. All right, so here's one for you to try. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8.00 atmospheres. So that's the pressure of the mixture. If the oxygen has a partial pressure of 1280 millimeters of mercury, what's the partial pressure of the helium? And the answers are all in millimeters, so they want you to get the answer in millimeters. So what are we going to have to do? Why don't you take a shot at it and just pause the video and come back and see the solution. That's going to be similar to what we had before. We're going to have to convert our atmospheres to millimeters, and that's what we're doing down here. So that means the total pressure is really 6080. Here's my 6080 millimeters of mercury. And then I can subtract the pressure of the oxygen from that, which is this guy here. And then I got that for an answer. It's pretty straightforward. Now this is where the medicine comes into play. We talk about oxygen and carbon dioxide in the blood, and that's actually measured by the partial pressures of each. And so in this diagram here, we have in the lungs, oxygen enters the blood and CO2 leaves it, and in the tissues, oxygen enters the tissue and CO2 leaves the tissues. And this is supposed to represent the tissues here, and these are the alveoli in the lungs. And so the PO2 less than 30 in the tissues, and PO2 is 100% in the alveoli. So your oxygenated blood is going to the tissues, and the reason the oxygen enters the tissues is because of the pressure difference. So oxygen flows into the tissues because the partial pressure of O2 is higher in the blood and lower in the tissues. And the gases flow from high to low pressure. CO2 flows out of the tissues, again because of partial pressure differences. And we can see that here in this slide. Oxygenated blood, let's say we have 100, let's say it's millimeters of mercury, and CO2 it's 40. And then we have deoxygenated blood, a lot less pressure, and you see the CO2 is up a little bit, not much. So, but in the tissues, it's different. So why does oxygenated blood release oxygen to the tissues? Look at the difference, 100 to 30. So it's going to flow from the blood into the tissues. Now for the CO2, it's 50 or greater. It's going to go then from here back into the deoxygenated blood, and you see it's even less as we go to the lungs. That's the reason why we can get these gases in and out, because of the pressure differences. And this graph or chart is telling you the same thing. Inhaling the air, here's the pressure of the nitrogen. Exhaling it, A little bit, kind of the same. So that means that some of the nitrogen is staying in our lungs, some of it might be dissolving into the bloodstream, but it's not having much of an effect because there's really a very small amount of it. And in the alveoli, inside the lung tissue itself, you see that it's a little bit greater than the expired air, but not too much of a difference. Looking for the oxygen now. You breathe in, here's the pressure of the oxygen, 160. 116 is what you're exhaling. That means the difference here is going into the tissues. So the alveolar air has 100 for the millimeters of mercury. So you notice that's a lot. That's less than what you're expiring. The carbon dioxide, you're breathing out. You're breathing in less carbon dioxide, breathing out more. That's what these numbers are telling you. And that's the end of the show.